Hello, everyone. In this video, what we're going to do is we will start discussing bond dipoles. This is something that, again, has its roots in a general chemistry concept of electronegativity. We've very briefly touched upon this earlier, but we're going to discuss this a little bit more because this is what will lead us into this concept of bond dipoles. So what is electronegativity? I think what you learn in Gen Chem is that it is, and this is true. Okay, so I'm just trying to like review it, but electronegativity is defined as the ability, okay, it is the ability of an atom to attract a shared, okay, that's an important word there. So a shared pair of electrons towards itself. So it is the ability of an atom to attract a shared pair of electrons towards itself. What does that mean? So when we have a bond, okay, let's say if we have two hypothetical elements, A and B, and if these are bonded to each other, if there's a covalent bond between them, okay, so this here is a covalent bond. We've discussed covalent bond before. Remember that these bonds are formed by sharing of electrons, okay? So these are formed by the sharing of electrons. So in this bond, and in fact, for every bond, any bond for that matter, there are two electrons. One of these electrons is contributed by A, the other electron is contributed by B. In an ideal scenario, because this is a bond that's formed by the sharing of electrons, in an ideal scenario, you would expect that these two electrons, because they are shared between A and B, you would hope that they would be found somewhere in the middle. Although realize that electrons are not localized in one place. They move around. But you would expect that the electron density from the bond, you know, so the probability of finding these electrons, that would be the highest somewhere in the middle between A and B, because we are saying that this is a covalent bond, which means it's formed by the sharing of electrons. However, that's not always true, okay? One of these elements, okay, depending on its electronegativity. So this is where the electronegativity concept comes in actually. So one of these elements, either A or B, might actually distort this electron density such that the electron pair or the electron density, I'm drawing the electron pair to represent that electron density, that the electron density or the probability of finding those electrons is higher next to that element. Now, I just arbitrarily drew the two electrons closer to B. I could have as well drawn them closer to A. Either one would have been fine. But what I'm trying to say here is the probability of finding those electrons, the electron pair which constitutes this bond, that's higher closer to B. So that means B is actually attracting this shared pair of electrons towards itself. And so when that happens, or if that happens, not when, if that happens, then we say that B is more electronegative. Now, what I also want you to remember is this is a relative concept. So in this particular scenario, we are saying that B is more electronegative than A, okay? In a completely different scenario, it is possible that B would be the less electronegative element. Okay, so for example, if we have a bond between some element B and another element D, and now D has more electron density around it, then that would make D the more electronegative element. But again, this is with respect to B. So that's something that you want to keep in mind. So essentially, electronegativity, like I said, it is the ability of an atom to attract a shared pair of electrons more towards itself, keep it closer to itself, so that the electron density from the bond, so this shared pair, again, that is the bonded pair of electrons. Those electrons are found closer to B. Okay, then we say that B is more electronegative. Now, what does that entail? You know, what does this lead to? So essentially, because the electron pair is spending more time near B, or the probability of finding that electron density is higher, closer to B, and since electrons are negatively charged, what that would mean is that B is going to have a partial or a slight negative charge on it. And we represent that by using this del negative sign. Okay, so del means small and the negative means a negative charge. So B becomes a slight negative, a partial negative. So it becomes a del negative. And A, it would become a partial positive. Okay, and that's because remember that the two electrons here, one was contributed by A, the other one was contributed by B. And instead of spending their time in between, in the middle, those electrons are now spending more time closer to B. So in some sense, A has lost its electron to some extent, not completely, but it is giving away that electron to B. So that's why A becomes a slight positive, partial positive, B becomes a partial negative. And so now if you relate this to like a magnet, okay, where you have poles, positive or north pole and south pole, or maybe electrical current, or either ways, okay, when you do that, what you notice is there is a positive end in your bond and there's a negative end, and we can show this using a bond dipole. Okay, so to show a bond dipole, this is the dipole arrow, so this is the bond, and this will lead to a dipole moment in this bond. But the bond dipole is shown by using this arrow, where the positive end of this arrow is on the del positive, and the arrow itself points towards the negative end. For this particular bond here, hypothetical bond between B and D, D is going to be del negative, B will be del positive. So the bond dipole here would be shown like this. Okay, and an understanding of this is important, because this is important when it comes to predicting reactions or reactivity of bonds within molecules. Okay, it is important to know where is the del positive, where is the del negative, okay, or which site is lacking electrons and which site has a higher electron density. So that's just a preview. So let me just draw out a few examples to show you how the bond dipoles would be drawn. And in fact, before we do that, we're also going to define something else. So electronegativity, and we're going to talk about the different bond types. Okay, so bond types that exist. And this bond types is based on the difference in electronegativity between the two atoms that constitute a particular bond. Okay, so the bond type is basically defined by the difference in electronegativity between the two atoms that are part of that bond. Okay, that are part of the bond. So based on this, so if our difference in electronegativity, okay, En is what it's not a very formal notation, but I'm just going to use En. If the difference in electronegativity is less than 0.5, then we say it is a covalent bond. If the difference in electronegativity is between 0.5 to 1.7, then it is defined as a polar covalent bond. In fact, before we move on, let me give you an example of a covalent bond. So an example would be a CH bond. So if you look at your table, if you look at any textbook, what you would notice is the electronegativity for hydrogen is 2.2. Electronegativity for carbon is 2.5. So if you notice, the difference between these two numbers is less than 0.5. So this is, we call it a pure covalent bond in some sense. What that means is the electron pair, which constitutes this bond, it spends its time, the probability of finding that electron density is exactly in the middle, sort of. That is what we're trying to say here, okay? And if the difference in electronegativity, as I said, was between 0.5 to 1.7, then we call it a polar covalent bond. Okay, it's a polar covalent bond. An example for this could be a carbon oxygen bond, although there are like other bonds also, but a carbon oxygen bond. Carbon electronegativity is 2.5. Oxygen's electronegativity is around 3.5. Okay, so the difference here is about 1, which falls into this range. And so this is a polar covalent bond. So when we say polar, we are actually implying a dipole. And so what that means is this more electronegative element has a del negative on it. The less electronegative has a del positive on it. And there is a dipole to this bond. So the positive end of this arrow, the dipole arrow, is on the carbon, which is partial positive. The negative end points towards the oxygen, which is partial negative. Okay, so this is the first scenario. This is the second scenario. And the third scenario is when the difference is greater than 1.7. Okay, if the difference in electronegativity between two elements is greater than 1.7. And in this particular case, we call the bond an ionic bond. We talked about this earlier. So these bonds are formed by a complete transfer of electrons. Okay, so something like sodium chloride. You can look up the electronegativities. In fact, I would encourage you to actually look it up. You know, sodium chloride, sodium fluoride, any of those things, you would notice that the difference in electronegativity between these two should be greater than a 1.7. So those bonds are ionic. So there is an actual positive charge on that sodium, a negative charge on the chlorine. Now, this is not a dipole because this is not a covalent bond. In some sense, yes, but an ionic bond is it is two ions actually. So we talk about dipoles when it comes to polar covalent bonds. That's when we talk about dipoles. Okay, so those are the three different bond types. So now let's look at some actual molecules, and maybe we'll try to draw the dipole in them. So let's say if we have chloroform. Chloroform, okay, which is CHCl3. So in chloroform, you have three carbon chlorine bonds. In fact, we should be able to predict the hybridization, and let's practice that. So predict the hybridization and draw an appropriate geometry. So if we write a Lewis structure for this molecule, this is carbon that's bonded to the three chlorines and the four hydrogens. So if you were to predict a hybridization, what would be the hybridization for this molecule, for this carbon here? Okay, the carbon has four groups around it. That means this carbon is sp3 hybridized. So the molecular shape is tetrahedral. So we're going to draw it as a tetrahedral molecule. So tetrahedron is best shown using these wedge and dash bonds in 3 dimensions. Okay, so that's a tetrahedral carbon now. The carbon is sp3 hybridized. Now, if you think about bond dipoles, that's what we're trying to draw here. There shouldn't be any dipole between carbon and hydrogen. That's a covalent bond, but the carbon chlorine bonds all have dipoles in them. And chlorine is more electronegative. So the bond dipole here is going to be pointing from the carbon to the chlorine for all of these bonds. Okay, they will all have a dipole, and it will point towards the more electronegative element. So the reason we are doing this is because the chlorine is more electronegative. Okay, another simple example that I'm going to use here is water. So water, oxygen with 2 hydrogens. Also realize that the oxygen has 2 lone pairs to it. Okay, and if we predict or determine the hybridization, this oxygen is also sp3 hybridized. Okay, and so we can again draw this using a tetrahedral kind of shape. So we have the hydrogen here, the hydrogen there. Okay, and going back to our previous lecture, remember that this is not a this is not exactly a tetrahedral. We say that the water molecule is bent because of the 2 lone pairs, and the bond angle is squished, so it is smaller than a tetrahedral bond angle. But if I were to draw bond dipoles here, hydrogen is less electronegative than oxygen. So in this particular case, the bond dipole is going to be towards the oxygen atom. Okay, the bond dipole would point towards the oxygen atom. Now, there's more that we can draw here. We can actually draw a bond dipole between, although it's not a bond, but we can draw dipoles for this oxygen and the lone pair. The lone pair is a pair of electrons that's negatively charged. Okay, so a dipole here would actually point towards the lone pair itself, because that's electron density compared to the oxygen. Okay, those electrons belong to the oxygen, but we can also draw a dipole for a lone pair from an atom. So that would be the bond dipole for a water molecule. So I hope this is helpful. So that's the concept of bond dipoles, and what we're going to do in our next video is use this concept of bond dipoles to actually determine or draw the direction of a molecular dipole, which is dipole applied to an entire molecule. Bye.